Hey guys, and welcome to our tutorial video on the selection sort algorithm. In this video we'll discuss the workings of the selection sort algorithm and also explain to you through a worked example how it actually sorts a list of numbers. We're going to divide this video into two parts. The first part of this video will be about the step-by-step worked example of the selection sort algorithm. This will help you visualize it and understand it better. In the next part, we'll actually take a look at the code for the selection sort algorithm. Alright, so let's begin. So here's the list of numbers that we'll be sorting here today. Now, the basic analogy or the basic concept behind the selection sort algorithm is to make a number of passes or a number of iterations over this entire list of numbers, and in each iteration it's going to find the minimum value and then swap that to its correct position. Alright, I'm going to show you this basically through this worked example. Alright, you'll understand this as we move on. Alright, so this is the initial condition for, or the initial state actually, for our selection sort algorithm. It's currently I is equal to 0 here, is currently representing the 0th pass, alright, or the first pass. 0th index or first pass is the same thing, alright, and the minimum value by default is the first value in this list, alright, by default. It's not the smallest value obviously, because we can see 1, 3, 4, 2, they're all smaller than 6, but by default as an initial value we pick the first value in the list. Alright, so let's continue. Now our job is to iterate over this entire list and search for the real minimum value. We're going to keep comparing it to each value in this list, and if the value is smaller, alright, if for example 9 is smaller than 6, it's not, but if it was smaller we would change the minimum value, right? The new minimum value would be 9. Alright, so let's continue. Now 9 is obviously not is not smaller than 6, alright? So let's move on. 1, alright, 1 is smaller than 6. So we're gonna swap out minimum value with 1, alright? So the new value of min value is now 1, okay? Next up is 3, nope, it's larger. 4 is also larger, 8 is also larger, 2 is also larger, and 7 is also larger. So now we're going to move on to the next pass. But before we do, we're going to do one integral step, right? One very important step. We're going to swap the minimum value, alright, in which case this is 1, with the index over here. So basically here we're going to swap min value, okay, 1, with the position, with the value actually at the 0th index or the ith index, okay, which is 6. So we're going to swap 6 and 1, okay, and this gives us this following list, okay. Now notice something, 1 is now at the start of the array, or in other words, the minimum value is now at the start of the array. So what does this mean? It means that 1 is now in its correct position, okay. It is sorted, because in any sorted array, the first value is always the smallest, okay. So just for visualization purposes, I'm going to separate 1 into a new array, alright. We're not actually separating it, okay, we're just doing this for visualization purposes, okay. And this over here is now the unsorted part, okay. And this is actually where we continue on to the next pass. And the rule is with the passes, since this is now I is equal to 1, we're going to start from the first index, okay, not the 0th index. So we're going to start from here now, because there's no point in starting from 1, because it's already sorted, okay. So we need to actually sort this now, okay. So let's just ignore 1 for a while. And now we've picked the first value over here in this search range, in this new search range, we picked 9, okay, because it's the first value. So let's continue. Alright, 6 was smaller than 9, so we've replaced the min value with 6, okay. The new min value is now 6. Let's continue. Okay, min value is now 3, 4 is larger, so we'll move on. 8 is also larger, so let's move on. Alright, 2 was smaller, so min value is now 2. 7 is larger, so let's ignore that. And now let's actually begin with the next swap, okay? So what is the ith value? It's 1, okay? And that means we'll be swapping the min value with 9 over here, because 9 is the first index. So we'll swap 2 over here with 9. And this gives us the following array, or list, okay? Let's move on to the next pass. Okay, the new min value is now 6. Okay, so 3 was smaller, so min value is now 3. And notice over here that I is equal to 2, okay, which is why we started from 6. right? 4 is larger than 3, so no change. 8 is also larger than 3, no change. Also no change, no change. So we'll now swap the min value 3, okay, with the value at index 2, okay. So that means we'll swap 6 and 3. Alright, now we have the following list, okay. Let's move on to the next pass. Alright, I is equal to 3, so that means we're on the 4th pass, okay. And the min value was once again selected as 6, okay. Let's move on. Alright, 4 is smaller than 6, okay, so it's now the min value. And next up is 8, 9, and 7, which are all larger than 4, so no change. Like we've been doing before, I'm going to swap 4 over here, okay, with 6, alright, because 6 is at the 3rd index, okay. And now we're at the 5th pass, alright, and we're half sorted already. You can see 1, 2, 3, 4. We have a very nicely sorted array forming, okay. Alright, min value is 6 again, okay. 8 is larger, 9 is larger, 7 is larger. So the min value is 6, and this is where actually we have an interesting scenario here where the min value is 6 and I is equal to 4, alright, is also 6, the 4th index. So basically we're at a situation where 6 is swapping with itself, alright. So basically there's going to be no change, alright. And now we're on the 6th pass, okay. Now the min value is 8, okay, 9 is larger, no change, 7 is smaller, so the min value is now 7, and now we're going to swap 7 with 8, okay, because 8 is at the 5th index, okay. And now we have just 8 and 9 left. 8 is the min value, alright, and of course it's smaller. And 8 will just swap with itself here because I is equal to 6, which is basically 8, okay, and the min value is also 8, so 8 will swap with itself, which means it's sorted. Alright, then only 9 will be left, which basically leaves us in a sorted position. Alright, we're done. So that's great. Let's move on to the coding part now. Alright, so here's our code for the selection sort algorithm. It's pretty short and simple to understand. Okay, so let's actually get into it. I'll just briefly go through it line by line now. Okay, here's the array of numbers that we want to sort. Okay, we pass that into our selection sort function over here. And now let's go up here. Here's our for loop, okay, this is the I for loop. This is the one that's responsible for making a number of passes over the list of numbers, alright. And over here you can see that we pick min index is equal to I. We don't do this, right? We don't do the first index, okay? We're not picking the first index of the array. What we're doing is actually picking the first index of that search range, okay? So for example, if I is equal to 2 and we're on the 2nd pass, we're going to make the min index 2. Okay, because the first 2 values will already have been sorted by this point. Okay, and here's the 3rd for loop. Okay, this one is responsible for individually going through each element in the list, okay, and comparing them. And we begin from I plus 1 because we don't want to start from min index. Okay, we have already assigned min index is equal to I, so there's no point in comparing min index to itself down here, okay, in this comparison. So in this comparison over here, if the value at j actually turns out to be smaller than the min index, okay, that we randomly picked up here as the first index, so then what we do is actually reassign min index, we make it j, okay, because this value is clearly smaller. So we reassign it. Now actually this much is all you need. Actually this over here, I could remove this right here and it would work. This is actually more of a optimization, okay. So it actually prevents unnecessary swapping. Now as you noticed back there when I was showing you the example, there were 2 scenarios, alright, 2 times it happened that the value ended up swapping with itself, right, where the I index and the min value, the min index basically were both the same, right. So this kind of scenario did occur. So what this code over here does, it says that only swap if the values are different, alright, if min index is not is equal to itself, basically. That's what this is saying. So that's why it basically prevents unnecessary swapping, alright. It reduces the number of extra operations that you have to do, alright. It's just a nice little optimization trick to keep in mind, alright, that's all. And with that we're actually done. Let me just run this once just so you can see it. And there you go. We have a perfectly sorted list of numbers right there. Alright. Okay, so let's just briefly discuss one or two things about the selection sort algorithm. For one, it's not really the fastest, alright, honestly. As you can see here, it uses two for loops, alright, two nested for loops, and the problem is that this gives it time complexity of a big O notation, n squared, alright, and n squared is well, it's a slow algorithm type, and as the number of elements in this list increases, then the time required to sort this will drastically increase along with the number of elements. For this reason, sorting algorithms with a time complexity of n log n are actually preferred. Of course, you don't have to worry about this for most cases, because chances are you won't be sorting something that's larger than 1,000 or several thousand, alright? So as long as you're within those limits, it's perfectly fine, alright? Since computers can execute billions of operations within seconds, alright? But if you're in a scenario where performance is a key, you're probably better off using something else, okay? And if you're actually interested, you can follow our sorting algorithm series, alright? Because we actually have covered almost a dozen different sorting algorithms, alright? So yeah, subscribe if you want to follow more of our content, and maybe I'll see you in a later video. Later.